Hello viewers, welcome back to the course on matrix computation and its application. So, today we are going to discuss a very important concept, that how a linearly independent vector can be made the orthonormal, and this process is given by the great mathematician Gram-Schmidt process. So, this process is called the Gram-Schmidt process. So, let us do them. Now, in the previous lecture we have seen that if we have a orthonormal basis, we have a orthonormal sets, vectors, then automatically these vectors are linearly independent, that we have seen. Now, the question comes that what about if the set of vector is linearly independent, can we say that they are orthogonal or orthonormal? This process, that if we have a set of linearly independent vectors, can we make them orthonormal to each other? So, that is what we want to do. So, this process, how we can make the linearly independent vector to the orthonormal basis, that is given by Gram-Schmidt process. So, let us see what is going to be in the Gram-Schmidt process. So, before that we will discuss about few concept about the projection. So, now I know that suppose I have a vector, this is my vector, I call it maybe V, and suppose I take the another vector, that is my vector U. Now, this is the angle between these two. So, I know that if I take the dot product U dot V, then this can be written as magnitude of U magnitude of V cos theta, and from here we can find that suppose we have two vectors, then it is equal to U dot V, and if we want to find the angle between these vectors, so this is cos inverse U dot V divided by this one. Now, we know that if U and V of unit magnitude, then this will be just equal to cos theta will be equal to U dot V. So, these things we already know. Now, what I want to do, I take the projection of this vector on the vector V. So, this is suppose O and this is A, this is my B. So, the position vector I am taking, the position vector OB, we represent by this as a vector. So, this is basically U, the position vector. Now, I want to take the projection of this OA. So, now I can write that OA. So, this OA I am writing in the direction of V. So, this OA is basically U. So, this is U I am taking cos theta. So, that is the projection I am taking. So, this is my OA, or means I am talking about the magnitude. So, this is equal to the magnitude of this one. So, if suppose I want to find out the projection of U in the direction of V. So, this is equal to, I am taking the projection U cos theta into the direction of V. So, I will take V direction. So, V hat is this one. Now, from here I can write from here u bar cos theta, u bar means this is magnitude. So, basically I told you that this is same as this one. So, in the vector form we always write with the 1 this bar. So, that is same as the magnitude. This double bar has the some advantage. So, that we going to discuss later on. So, this is equal to this. Now, this V is, I know that this is equal to V divided by its magnitude. Now, from here I can write from here. So, this one. So, I can write projection of u on V, it can be written as u, and the cos theta we already know from here. So, I can write here u dot V divided by this into V magnitude V, and this will cancel out. From here it become u dot product of V divided by length square. Now, if V is 1, so it is a normalized vector. Now, from if it is this, then my projection of u on V becomes just taking the dot product of u with V multiplied by V, because u dot V is just the dot product. So, it will give you that the quantity, and V is the unit vector. So, that will be the projection vector of u in the direction of V, where V is a unit vector. So, this is how we take the projection of a vector over the another vector. For example, let us take one example. Suppose I take it is r square. So, it is x axis and it is y axis, and suppose I just take one vector. So, I call it maybe 2 3. So, this is my vector. So, I call this vector as my vector u. Now, I just take the projection of this u on x axis. So, I know that x axis, so this the vector I am taking in this direction is a standard vector. So, we call it E1. So, I know that E1 is the unit vector 1 0 and E2 is 0 1. So, these are the standard bases in the R2 that we already know. So, I just take the projection of this one. So, I am taking the projection of this along the x axis. It means if I take u and I take a vector in the x axis, so that vector I know that is E1. So, if I take the dot product with E1 and then I write E1, so that will become, so I am taking u dot product with E1, so it will be 2 and E1, and it means it becoming 2 0. And you know that if I take the projection on this one, so this point will be 2 0. Similarly, so suppose it is O, it is A, it is B. Now, so my OA, so I take the projection. So, this projection vector is my OA basically. So, this is a projection of u on x axis, and that should be 2 0. Now, I take the projection of u on y axis. Let us take this one. So, this is equal to, I am taking the dot product of u with the the vector in the direction of y axis. So, I am taking the unit vector, that is the standard basis I am taking, and this is E2. So, if you see from here, this will be equal to 3 E2 and that will be 0 3. So, this is my projection vector of u on the x axis. Also, so this can also I can write, let us see what will happen if I take u and I will remove this part from the u. So, I will just write u minus projection of u in x axis, and I know that x axis and y axis are orthogonal to each other, that we already know, that E1 is orthogonal to E2 and this is. So, I can say that E1 and E2 are orthonormal basis and they are also standard basis, that we already know, also called standard basis. So, that is why we already know that working with the standard basis is much easier as compared to the other basis. So, instead of the standard basis, we are going to introduce other type of bases which have the same property as the standard basis. So, these are the orthogonal to each other. Now, I see what is happening u minus projection of u in x axis, because if you see that this is my u. So, I can write this as a u cos theta component and u sin theta component, that we already know, because it is a right angle triangle. So, using the Pythagoras theorem, we know that u cos theta square u sin theta square, that is equal to u square. So, this is a Pythagoras and this is happening because they are perpendicular to each other. So, these bases are here. Now, I am taking this projection on this. So, let us see what is going to happen here. My u is basically this vector 2 3 minus I am taking the projection of u in the x axis. So, this part I am removing from here. So, basically I am removing 2 0 from here and that becomes, so 2 minus 2 and 3 and I am getting this part. So, from here you can say that, now from here I can say that u can be written as, if I taking the projection of u along v, plus I can write u minus projection of v. It means, so this is the projection in the perpendicular vector to u. So, that we can say. So, this projection of u we are taking in the direction perpendicular to the vector v. Okay, so, that is here we are doing. So, we are taking the projection of u along v and this is the projection of u in the direction perpendicular to v. So, this is my projection in the direction perpendicular to v, that is perpendicular to this. So, I am taking here as a y axis. So, that is my u. It means I can split my u into two parts, one in the direction of v, another in the direction perpendicular of v. So, here I am taking v, maybe I can just, instead of v I just write x axis, because here we are talking about x axis. So, I can talk it here x axis, x axis. So, this is a projection in the y direction. So, which is a perpendicular to x axis. So, this is the way we are doing it here. Now, I know that if v is a unit vector, then the projection will be in this form. and this is also we have discussed that it is a component in the direction of x axis and in the component in the direction of perpendicular to x axis, that is in the y direction. So, we can split the vector like this one. Now, so from here let us see what is going to happen in the case of 3 vectors. So, this is the 2 vectors we have taken. We have 2 vectors. So, let us consider set of 2 linearly independent vectors. So, suppose I take the set as V1 and V2. This is linearly independent. Now, from here if it is linearly independent, then I can normalize this one. So, we can normalized. So, how we can normalize V1 and V2, and from here I can write my U1 as V1 divided by its magnitude, or maybe 1 or U2 I can write V2 as this one. So, from here I know that U1 and U2 are Li and normalized. So, nothing has changed, only the length has become 1, that is it. Now, I take the set V1. So, V1 is non-zero, it is linearly independent, that I know. So, V1 I have taken, that is not 0, I know that. So, only one vector V1 is linearly independent, that I know. Now, so this is what we are going here. This is my V1, some vectors, and I am taking the line passing through this line, vector V1. So, suppose this is my V1, this is my origin, I am taking a line passing through this V1. So, this is the line I am taking. Now, suppose this is unit vector I am representing by U1. Now, from here one thing is true, that if V2 is linearly independent to V1, then V2 cannot be on this line, because if V2 lies on this line, then they will be linearly independent. So, maybe it cannot be on this line. So, suppose it is lying somewhere here like this one. So, this is suppose my V2, because it cannot be parallel to V1 or lying on this V1. So, it is tilted. So, whenever it is tilted, definitely it will cut the line here. So, suppose this is this one, and I call it, this is the O where it is cutting. Now, from here I can take the projection of this on this line passing through the vector V1. So, suppose this is the basically my line is there, and I am just taken the V1 vector, because I can write the line L as some scalar, maybe I can take it some alpha into V1, where alpha belongs to real line. So, this is the line. Now, I have taken this one. So, I am taking the projection of V2 on the V1. So, now from here I know that the projection of V2 on V1, that will be equal to, I am taking the dot product with the vector V1, then I am writing V1 divided by the magnitude square. So, this is what we have defined from here, that if this is of this form, then we can write like this, or maybe I can write. So, this is we have written, or we can write it as V2 dot V1. So, I am taking the V1 and U1 is the unit vector in that direction. So, maybe I can take it as U1 here, no problem, into U1, and I know that the U1 magnitude square, but this is equal to 1. So, it is V2 dot U1 U1. So, this is my projection of V2 in the direction of U1, or I can call it the projection of V2 in the direction of V1. So, this is the way we have taken projection of V2 on V1, and I will take the vector u in that direction. Now, from here, so this is my projection. Now, I want to write, so this is suppose OA and B. Now, I want to write what is my AB vector. So, that is the perpendicular vector we are going to take. So, what I am going to do is that I am taking my V2 and subtracting the part of projection of this along the direction V1. So, this is I have taken V2 minus V2 dot U1 dot product U1. So, this is my AB. So, it is V2 minus the projection along U1. Now, from here you can see that, so I call it maybe some Y2. Now, from here you can say that now Y2 is orthogonal to, so this is orthogonal to V1 or U1, because this is my Y2 I have taken, I call it my Y2. So, this Y2 is orthogonal to V1 or U1. Okay. So, from here, so how I can write Y2 directly? So, Y2 is basically V2 a vector minus its projection along the line U1 U1. So, this is I have taken my Y2. From here Y2 is orthogonal to V1 or U1, because U1 is just unit vector. Now, what do we do that? Now, we normalize Y2, and from there I call it Y2 divided by its magnitude. So, I call it U2. So, from here I can say that the vector U1 and U2, so these vectors are orthonormal to each other, or the orthonormal vectors are orthonormal. So, I just stop here and write it orthonormal, but orthonormal means that these vectors are, so we started with the linearly independent vector V1 and V2, and then we from there we have constructed the vectors which are orthogonal to each other and having the magnitude 1. So, basically what we have now, we have started with this one. So, this become the orthonormal basis. So, if I have a vector with two bases, the basis having the two vectors, then by this process we are able to make it orthonormal. Now, I consider the third one. So, let us take the third part. So, this is we have started with 2 vectors. Now suppose we have set of 3 vectors. So, suppose I take the basis with vectors v1, v2, v3. So, this is a basis and suppose this is Li. Now, from here I know that I will take my vector v1, I will normalize it and I will call it u1. Then I will take the another vector y2 that will be orthogonal to this one. So, I will take my v2 minus v2 taking the dot product with u1, u1, and from there I will write u2 that is y2 divided by its magnitude. So, it is normalized vector. Now, u1 and u2 are orthonormal vectors. Now, what about the third one? So, let us take the v3. So, in this case what we are going to do is, it means that I have a vector, suppose I represent suppose I write here, this is my suppose u1 and I take another vector which is my u2, they are orthogonal to each other, and suppose they make a plane. So, I make a plane from these 2 vectors. So, this is my plane. Now, in this plane if I take the linear combination of this one, that all the vectors will lie here. So, I can say from here that this is a subspace, basically subspace of R3 I am taking, because I am taking 3 vectors. So, using 2 vectors from the basis, they will make the subspaces. Now, I take another vector v3. So, this v3 is linear combination of v1 and v2. This v3, v1, v2, v3 are linearly independent to each other. So, definitely the v3 cannot be a linear combination of v1 and v2, because if v3 is lying in this plane made by v1 and v2 or u1 and u2, then they cannot be linearly independent. So, from here I can write, now we know that since v1, v2, v3 are linearly independent, which implies, so it means that they cannot be coplanar, all the 3 cannot lie in the same plane. It means that v3 cannot lie in the plane span by v1 and v2. So, it means that I just take, so this is my u1 and u2 and I can extend it to v1 and v2, no problem. So, suppose this is my v1 and this is my v2, no problem. So, my v3 cannot be in this line, in this plane. So, I just represent by this is my suppose v3. It is not lying in the plane made up of u1 and u2, and suppose I take the projection of this on this plane. So, this is my projection. So, this is the projection we have taken. So, I call this as, suppose I call it O A B. So, from here I can write that from here O A, this is what I am writing, that is equal to projection of vector V3 on the plane spanned by V1 and V2. So, it is the plane spanned by V1 and V2, and this is just I am putting taking the projection of this one. So, that is OA, and AB is the projections in the direction perpendicular to this subspace. Now, from here, any vector say y in the subspace spanned by V1 V2. So, I can write this C1 V1 plus C2 V2, and these are linearly independent to each other. So, from here I can call this y as y taking the dot product with u1, that is a normalized vector, in u1 plus y dot u2 u2. Okay, so, spanned by V1 and V2, or maybe I just instead of this one I take u1 u2. So, I can write from here as linear combination C1 u1 plus C2 u2, and u1 and u2 I know this is the normalized vector we have taken, and from there I also know that these coordinates C1 and C2 can be found using this formula. So, from here now I can write, so I need a vector which should be a perpendicular to this one. So, this one I need to find out, which is a perpendicular to the plane passing from u1 and u2. So, this vector, so I call this vector as maybe y3. So, from here I can find now y3 is a vector perpendicular. So, this is the sign of perpendicular to the plane spanned by u1 and u2. So, how I can find? So, the same way we will find out. So, I can write phi 3 as, now I have a vector v3. So, from the v3 I will subtract the projection of v3 on the subspace. So, the which subspace? The subspace spanned by this one. So, and subspace is spanned by from here. So, now from here I can write that I can write my v3. So, this is my y3, and how I can find this one? So, v3 I am taking the span. So, this one I can write as v3 u1 plus v3 u2 u2. This is what we have written, because I am taking these projections here. So, if I want to take the projection of this one, so that projection is basically a linear combination of this. Now, I want the projection, instead of y I will just write v3, because I need the projection of v3 on this plane. So, I will take v3 over this plane. So, this is v3 dot u1. u1 plus v3 dot u2 u2. So, this is the projection on the plane and that is v3. So, now from here now y3 is perpendicular to u1 and y3 is perpendicular to u2. Now, what I do is that I will take y3 and divide by its magnitude and I call it u3. So, from here now I can say that my vectors u1, u2, u3 are orthonormal, because they are perpendicular to each other and their magnitude is also 1. So, this is the basically how we can proceed for making the given linearly independent set to the orthonormal set. So, let us do this one again. So, I will write here the process that is called the Gram process. So, what we are going to do in this case, suppose we have a basis, I call it V1, V2, Vn. So, this is a basis of a vector space V. So, it is a n dimensional vector space. Now, what we need to do, so we want to convert basis B into orthonormal basis. So, this is done by the Gram-Schmidt process. So, how we are going to do is that, so this is the procedure. Step 1, because I will choose the vector v1. So, I will take the vector u1 as v1 divided by its length. So, I will make u1 is a vector, that is a unit vector. So, u1 is a normalized vector. Step 2. Now, in the step 2, I take the vector y2, this is equal to v2, this vector. I want to make this vector orthogonal to u1. So, I will take v2 minus v2 dot u1 u1. So, I have from the v2 I have removed the projections of v2 on a u1. So, I have removed that projection. So, that become the perpendicular part. So, y2. From here I will call u2 as y2 divided by its projection or its magnitude. So, that become the normalized. Then step 3, I will take y3 as v3 minus its projection on the plane made by or spanned by u1 and u2. So, that will be taking its dot product with u1 plus v3 u2 u2. So, it is a projections on that plane. I am taking v3 minus of that projection. So, this is perpendicular, and from here I will normalized. So, I will make it u3, that will be my y3 divided by its magnitude, and we keep going like this one. So, in the end I will get yn. So, what is yn? It will be Vn minus, from here I can take the summation. So, I am taking the Vn dot product with ui. Ui means the vectors, all the vectors I from 1 to n minus 1. Like here, when I am talking about 3, so we are going up to 1 and 2 only. When I am talking about 2, I am going only up to 1. So, I am going here into ui. So, this is we are subtracting, and that is my nth yn. This I can write, and from here I will write my un is equal to yn and divided by its magnitude. So, from here, after doing all this calculation, now we get a new basis of vector space V. So, I call this new basis as, let us call it, I will write u1, u2, u3, un, a new basis of V. So, let us I call it, maybe I should call B1, or I should represent by S, close to the standard basis. So, I represent by S. So, now we take a new basis of vector space V, that is S, which is orthonormal. So, these are orthonormal. So, we have started with a linearly independent basis, and we convert that one into the orthonormal basis with the help of Gram-Schmidt process. So, this is the benefit of the Gram-Schmidt process to convert or to transform a given set of linearly independent vectors in a given vector space to a orthonormal set of vectors. So, I will stop here. So, in the today's lecture we have discussed that if we have a basis for a given vector space, then how we can convert that basis into the orthonormal basis of the same vector space, and that process we have discussed is the Gram-Schmidt process, that is going to convert the given set of bases into the orthonormal basis, and in the next lecture we will continue with that one. So, thanks for watching, thanks very much.